This is problem 81 of Neetcode with 50 max area of hyphen, so let's read it together. You are given a matrix grid where grid at the index I is either a 0 representing water or it's 1 representing land. An hyphen is defined as a group of ones connected horizontally or vertically. You may assume all 4 edges of the grid are surrounded by water. The maximum area of an hyphen is defined as the number of cells within the hyphen. Return the maximum area of an hyphen in the grid. If there is no hyphen, return 0. Okay, so let's use the React technique to solve this problem. And the React acronym starts with the R, and the R stands for repeat the question. So let's go ahead and repeat it. So basically, we are given a 2D grid of binary values where 1 represents land, 0 represents water, and we know that an hyphen is formed by contiguous ones connected horizontally or vertically. We are to compute the maximum area among all hyphen in the grid. The R is simply the count of the land cells within a connected hyphen. Okay, and if there's no land, you have to return a 0. Great, so now we did the R. Now let's go to the E of React. So the E is giving example. Let's go take a look at this example. So we know that hyphen connected diagonally do not count as contiguous hyphens. So this is an hyphen by itself, like the one here that is in the first column of the second row. And now we know that we have an hyphen that is connected through basically all the rows. So at the rows at column 2 and 3, and now we have row 2 at column 3. Now you have row 3 at column 2 and 3, and then row 4 at column 2. And now we know that for all the rows at the column 5 we have another hyphen. Okay, and if you count all these values, like for example, if I just go for the orange hyphen here, I can see that you have 6 ones connected. So the length of this hyphen is 6, and this is the greatest. So we have to render it. Okay. Well, with that being said, let's also discuss an edge case that is not shown here. The edge case is basically if they're all zeros, and if they're all zeros, we have to handle this. Okay, so we're gonna have to return 0, not null or none. We're gonna have to return the integer is 0. Great. So now let's go for the A of React, which is approach. So for the approach, we are gonna iterate through the grid, and upon encountering a 1, we'll initiate a depth first search, and we're gonna explore all the connected hyphen, either horizontally or vertically. And we're going to compute the area of the visited 1. And during the traversal, we are going to mark the cells that we visited. So we're going to turn them into 0. So we know that we are not going to go just do some ping pong between 2 ones that are connected horizontally or vertically. We're going to set it to 0. So this is how we are not going to enter an infinite depth first search function. Again, we're going to maintain the global max area variable. After each depth first search, we're going to update the max area. So we're going to use the max function in Python to see if the area that we had in this current hyphen is greater than the previous one. So now we're going to jump into the C of React, which is the code. So let's go ahead. And first, we want to keep track of a measure or of a row in our columns. I will do this by calling rows and calls, and we know that rows is basically going to be equal to the length of the grid that we are given, and the calls is going to be equal to the length of any rows, meaning that we can say length of a grid, and let me pick the index 0. All right, cool. With that being said, we can create a depth first search function. So let's say dfs, and we can pass this for now because I want to explain another crucial aspect of this algorithm. So in this algorithm, we're going to initiate a max area. So let's call this the max area, and it's initially going to be equal to 0. And now we're going to go for every single row, and in every single row, we'll go for every single columns. All right, so let's just do this right now in code. So we're going to say for C in the range of our variable. Well, let's first say let's first go through every row. Pardon me. So for all the rows in the range of the rows, so what we created above, which is the line of the grid. And now for every rows, we can go through every column. So we're going to say for C in the range of calls. All right, so good. We get this. Now let's explain what is the next step. Is that for each of these basically each of these squares within the board, well, we're gonna have to react if we see a 1, okay? Because as we discussed in our earlier discussion, if we have a 1, we're gonna go through all the connected ones and we're gonna turn them as 0. So every time we are looping through the rows and the columns, well, we are never gonna encounter an Iceland we previously saw, because the Iceland that we previously saw is now synced down. They're all zeros, so it means that if we see a 0, right? So we're gonna like the English sentence if we see a 0 is translated to if the grid at the row and at the column, right? So if we see a 0 at the case we're at, so that will be equal to well, in fact, if we see a 1, because if we see a 0, we just want to pass. There's nothing we really care about. So if we see a 1, well, then we're going to set our max area to be the max between the previous max area and also the call of our depth first search function. So DFS with that row and that column. So now we know that our depth first search function will return an area, okay? And that's why we're using this. And at the end, we can return the max area, knowing that it's gonna actually give us the maximum area of any Iceland. And now we can, well, first insert the parameters in the depth first search function. So first we have the rows and the columns, and now on each calls, we want to do 2 things. Either we check if we have an Iceland. So if we are in the board and there is an Iceland or 1, we'll want to go see its neighbor to the right, its neighbor to the left, its neighbor up, its neighbor down. Only if we are in the grid and the value at that position is 1. So we're going to do this by saying if basically row is greater than, if row is smaller than 0, and notice that now I'm writing all the edge cases where we are going to have to return the function. So I'm going to write like basically if we're out of bound in the negative values, or if we're out of bound in the positive values, or if the values is actually 0, so it's not 1. All right, so in all these cases, we want to return. We don't want to keep going the recursive call. So we're gonna do that for the columns as well. So if C is smaller than 0, and notice I'm using or because we only need to have one of these statements true to actually know that this position is not a valid position. So we're going to return the call. So if the row is smaller than, if R is smaller than 0, or C is smaller than 0, or R is, let's say, greater or equal to rows, or same for the columns. So if the column is greater or equal than the calls, because we know that the last index of the index of the last rows is going to be equal to the length of the rows minus 1, right? So if R is equal to rows, it means that that R is the same as the length of the row, or the length of the grid. So we are out of bounds, okay? And let me just write this in 2 lines, so it looks a bit cleaner. All right, and what is the last statement that we want to do is what if our grid, right, at this row and at this column, what if this is, well, let's just say not equal to 1, okay, to avoid any edge cases. So if this is not equal to 1, right, in any of these cases, we are just going to return our call. Great. And now that we are handling all the wrong positions, we are we are gonna start to sync down every value. So now my current item at this row and at this column, well, I'll set you equal to 0. So I'll sync you down. And after this, we're gonna use a return statement, and we're gonna use basically a 1 to state this current item, which is an area of 1, and we're gonna do that plus the result of the DFS for each possible directions that we can take. So on each recursive calls, we're gonna add 1 if you found an item, or we're not gonna add 1. So at the end, we're gonna return the actual area of the current item that we are on. Let me just copy this times 4. So all right, so now we have to think, what can we do? Well, we first want to be able to go down, so we're going to increment the row by 1. We want to go up, so we're going to decrement the row by 1. We want to go to the right, so we're going to increment the columns by 1. And you want to go left, so we're going to decrement the columns by 1. All right, so with that being said, we are going to return basically the area of this, and after this we're gonna set the max area to the maximum between what we previously had and this recursive calls that we just did. So let's submit this. Hopefully it's gonna work. So for some reason I had an equal statement. Pardon me for this. So let's test this again. We have an error. So all right, so let's. Okay, so the error I did here is that if we are not in a valid position, I'm simply returning the call, but I need to return 0 so that we know that this is not an item and we don't want to increment the count. So let's submit this again, and it works. Okay. In terms of space complexity and time complexity, well, we know that we are going to visit every single cell, so this is going to give us basically a big O of rows times calls, or times n. And in terms of space complexity, well, in the worst case, because we're using depth first search, which is using a stack, so we're going to have to go through every single value, so it's going to be also, in the worst case, m times n. Alright, so with that being said, I hope you learned from this video, and I hope to see you in the next one.